the current I flowing through the electrical circuit in a fan t milliseconds after it is switched off is given by I equals 320 times 2 to the power of minus 0.5 t milliamps. Milliamps is a unit of current. Part A, we need to find the initial current in the circuit. Is that word initial again? Part B, find the current after 4 milliseconds, 10 milliseconds. Part C, graph I against T. I'm not going to plot a graph. I'm not testing if you can plot. Not now anyway. But we are testing, can you use the calculator? Can you do a sketch? Can you solve the problems? And Part D, use technology to find how long it takes for the current to drop to 50 milliamps. So note that this current is actually going down. You know it's going down for two reasons. Firstly, it's because we've switched the thing off, so you would expect the current to gradually leave the circuit. And secondly, you've got this negative power. So when you've got a negative power in there, it's a decay thing. It's because, remember, it's a reciprocal thing, a negative power. We'll have a look at the graph anyway. It'll be interesting. So part A, find the initial current. So the initial current is when t equals 0. So when t equals 0, we need to find the current. So I equals 320 times 2 to the power of 0 minus 0.5 times 0. Well, minus 0.5 times 0 is 0. 2 to the power 0 is 1, and 320 times 1 is 320. The units are milliamps. So part A, easy enough. B and C, we are going to need the calculator. So B, we're going to need the calculator. So find the current after 4 milliseconds, 10 milliseconds. So we're just substituting. So we're finding sort of I4, something like that, or when t equals 4. So I must equal 320 times 2 to the power of minus 0.5 times 4. And again, personally, I feel safer putting a bracket. With a particular calculator I'm using, you don't need a bracket, but some calculators, it doesn't necessarily, it's not obvious that the exponent is the exponent, but a bracket will make you more comfortable. It will certainly never make the thing wrong, having a bracket, as far as the calculation goes. So let's put it in there. So 320 times 2 to the power of, open bracket, minus 0.5 times 4 times 4, close the bracket. And that gives us 80 milliamps. Okay, part B2, 10 milliseconds. When t equals 10, I equals 320 times 2 to the power of minus 0.5 times 10. As I said in the last video, you could have used potentially a table mode for repeated calculations. If it wanted a lot of these, you should definitely consider a table mode, or graphing the function and using the trace feature where you can just put a value of x in, it gives you the y. But seeing as there's only 2 and I want to show working, I'm doing the substitution. But what we can do is use the up arrow and the left arrow, and we can go back into here and just delete the 4 and change it to a 10. So get rid of the 4, change it to a 10, execute, and that gives me an answer of 10 milliamps. Just make these answers clear. Okay, so part C, graph I against t. So we're just going to put it in the calculator. So menu, go to graph, and if you have old graphs, you need to delete them. Get rid of every graph in here, it would be my recommendation. Go up to the top and we want 320 times 2 to the power of, okay, I'm using a bracket, you don't need it for a good nice modern calculator like this, but I'll use it anyway. So minus 0.5 t, well we don't have a t, well, we don't really have a t easily available, we're going to use an x. Close the bracket, execute and draw, and you'll see it looks ridiculous, and the reason why it looks ridiculous, you can just about see a really flat looking line when it definitely shouldn't be a flat line. It's because of this scale up here. So I've got a really high y value. If you look at the numbers here, well, when the maximum value is 320 milliamps, this is decaying, it's getting less, so we certainly don't want to be much higher than 320 on the y's. So what we're going to do, go to the V window and we're going to go straight to that Y max. So at the moment it's on 100,000. So let's set it to 350. That would be quite nice. You don't want to set it to 320. It's good to have a bit of room up the top. So 350. Y min minus 2. I think that's okay. X max. We don't really know about X max until we do know. So 10's probably reasonable. And we certainly don't need anything in the negative. So execute and draw, and now you can see this exponential decay of current. So what you do, you switch the switch off and the current in the circuit just goes away. So you're losing more current at the start, and then it's going away at a slower rate as time goes on. Time's on the x-axis, of course. So that's the graph. I'm not going to plot it yet, but I certainly will plot it for part D, or sketch it, sorry. So use technology to find out how long it takes for the current to drop to 50 milliamps. So we're finding out, well, when does 320 times 2 to the power of minus 0.5x, when does that equal 50? So what you need to do, we've already got one graph in, we need to exit and go to y2, and we just want it to be 50. So we're going to draw y equals 50, execute, draw, and we can see there's an intersection there. Now remember, we need some working. This is why you can't just use a solver. You shouldn't just use a solver, not advisable. I'm going to draw a little axis there and there. Going to draw my decay function, something like that. And I might even put this 320 on there, so 320, just because it's such an easy point to put on. So that's the decay function. And then you've got y equals 50 here. So 50. And we're interested in this point. So we know that the y value is 50. What we don't know is what x value makes that true. That's what we're trying to find out. So we go Shift G solve, intersection. And you can see x is 5.35614. I think that's a 1. So we'll go 5.3561. Something like that. And did it ask for an amount of accuracy, specific amount of accuracy? It didn't. So if it doesn't specifically say something for the IGCSE, you should assume 3 significant figures. So this is going to be 5.3. Well, the first significant figure is the 5. The 6 will make the 5 round up, so we will say 5.36. And careful of the units, it's not seconds, it is milliseconds. So it's quite a short amount of time. And that's how you do. This is how you graphically solve questions that you would really struggle to do without using a graphical approach. You will become more and more familiar with logarithms, and that's how you can kind of get exact answers, but they're not necessarily very nice to look at, the exact answers. So right now this is a really good approach, and it will be really useful for the IB as well.